we're going to continue talking about our intermolecular forces. I believe we left off here last time. Remember, we said that our intermolecular forces are so important because they are going to determine the interactions between our biomolecules. So it's very important that we have a good understanding of our intermolecular forces. Hydrogen bonding between water, between other materials that have an electronegative atom that's covalently bound to hydrogen, and then another electronegative atom, those will affect the properties. So we saw that how water has 4 hydrogen bonds. It's more than other molecules that can also that are also the similar size and shape. You can see that the melting point for our water is so much higher. And why is that? What is happening during melting and boiling? We're breaking our intermolecular forces. And so it's going to take a lot more energy to break the intermolecular forces with water because it has the hydrogen bonding, which is an especially strong intermolecular force. And so water doesn't behave like the other molecules that have like shape and molecular weight because of this hydrogen bonding. It's really apparent with our methane. So let's talk about hydrogen bonding other than just with water. We have a lot of alcohols in our monosaccharides and other molecules. So you will see the hydrogen bonding with water and between water and a hydroxyl group, water and a carbonyl. Carbonyls you'll see in an aldehyde, ketone, acid, ester and amine, or an amide, I'm sorry. You can see the hydrogen bonding between an amino group and a hydroxyl group, and between an amine group and a carbonyl, and between an amine group and another amine group, another nitrogen-containing group. So it's not just limited to water. Hydrogen bonding is happening throughout our biomolecules. And which molecule or which biomolecule do you think has a lot of this type of hydrogen bonding with the nitrogen-containing bases? Amino acids, you'll see especially this one, and DNA, yeah. And proteins and nucleic acids, it's very important. Now, again, our weakest intermolecular force are the van der Waals, and there's 3 main types. Either a dipole, or you can add on to this an ion dipole. All right, you can see that a carbonyl is a dipole. The reason why we call it a dipole is because there's a permanent shift in electron density towards the oxygen. And so the oxygen is going to be electron rich, as apparent by the delta negative, and the carbon is going to be permanently partially positive. So when another carbonyl comes around, the negative part of the carbonyl is going to be attracted to the positive part of the carbonyl. And that's going to set up that attractive force. That's going to keep those molecules together. Now, a dipole-induced dipole is something where a dipole, a permanent dipole, comes by a nonpolar molecule. And what happens is you have an electrostatic repulsion between the electron density in the oxygen and the electrons in the nonpolar molecule. It causes the electron density to move towards this side of the molecule. Remember, we're dealing with orbitals. And we can find the electrons in any spot in those orbitals. It's all chance. But there's a natural swishiness to those electrons in a nonpolar molecule. And so we're going to cause an induced dipole or an induced reaction to a dipole going by a nonpolar molecule. So then this one becomes a dipole. this nonpolar methane becomes a dipole, where we have a negative side and a positive side. Once this moves away, it will go back to being nonpolar. Now, because we have a natural tendency for electron density to be on one side or another side of a molecule, we can have a temporary dipole happening, where two nonpolar molecules will come together, and then the protons on one molecule will attract the electrons on another one and cause the electron density to approach the other molecule. And that's an induced dipole. There's, remember, a natural swishiness to it. So if these electrons get attracted to the protons on this molecule, we'll end up with a dipole on this molecule. And then it will induce another dipole on this side. So know that nonpolar molecules have this sort of swishiness of their electrons. And it will cause a very, very, very weak, but nonetheless attractive force. Now, we know that nonpolar molecules have the lowest boiling points. And that's because this induced dipole or induced dipole attraction, we also call this dispersion forces in general chemistry, is the weakest force. And so we will see it broken easily. These molecules have very low melting and boiling points. Any questions about this? You guys good remembering our general chemistry? If you're still having trouble, I strongly encourage you to go back to your General Chemistry 1 book and read the chapter on intermolecular forces. It will definitely be worth your time to read that. And then you can come see me with anything that you don't understand. But remember when I was talking about fatty acids, and I said that the nonpolar tail attracts to each other, and the longer the tail is, the more attraction, and the higher the melting point. So we can see that if we only have a short tail, okay, say it's this long for our fatty acid, it'll be easier to break apart than a longer tail. So we see with our fatty acids, as the chain length of that nonpolar part of our fatty acid gets longer and longer, we see a higher and higher melting point. I like to think of dispersion forces as Velcro. Right? To me, it's Velcro. And with Velcro, the more points of contact, the harder it is to pull apart. I finally moved out of Velcro shoes in my family. They all now wear tying shoes with the Velcro. That's a big step. All right, so the dipole, remember, is a permanent thing, where the induced dipole is a temporary thing. Let's go back to ion dipole. This is what drives things to be dissolved in water. So either an ion or another dipole will be surrounded by the opposite side of water. Remember, water has a negative side, the oxygen side, and a positive side, the hydrogen side, because it is a bent molecule. So when you have, say, the salt, KCl, potassium chloride, gets dissolved into water, and it dissolves. What happens when it's dissolving? Well, the potassium cation gets surrounded by the negative side of water, and the negative anion, chloride, gets surrounded by the positive side, water. And this will happen also with dipoles, with polar molecules. An alcohol and a ketone, they will also have this attractive force, and it helps dissolve. One intermolecular force that we don't really talk about too much in general chemistry is hydrophobic interactions. And you may not have ever heard about this, and it is a source of confusion for many people. They don't really understand, why does oil and water separate? Why, when you don't shake up your salad dressing, do you end up with a salad full of oil? That's right, because the oil's on top. But why does that happen? You need to shake the salad dressing to get little droplets of the oil throughout. You need to put energy in. And the reason why is when you have something nonpolar, say like oil, fatty acid here, and it's nonpolar, what happens is around something that's nonpolar, we get this ordered cage around the nonpolar droplet. And what do we know about order or entropy in nature? Is it favored or not favored? It's not favored. We go from order to disorder, just like our lives. And it takes a lot of energy to put in that order. So we do not want to have anything nonpolar dissolved in our aqueous environments. So what happens is we try to get the least amount of surface area, the least amount of ordered cage. And so if you have lots of little droplets compared to one layer, which one has more surface area, the little droplets or the one layer? Think about your salad dressing. The little droplets, there's hundreds and hundreds of little tiny droplets of the oil, and those little droplets, those circles, have a lot of surface area compared to the one layer in between your aqueous on the bottom and your oil on the top, your nonpolar on the top. So between your vinegar or aqueous part of your salad dressing and the oil part, along that surface, you have this ordered cage of water. And that is the minimum amount of order that you can have in your salad dressing. So just like in our salad dressing, nature is going to try to minimize that. So when you pass your salad dressing, make sure you shake it up for your table mate, right? So that they're not pouring oil. People think that nonpolar molecules attract each other. There is the attraction between the dispersion forces, but it's really at the hydrophobic interaction that causes the oil droplets to coalesce. That is the real driving force. It's an entropy-driven process. So thinking of that, thinking about dissolving water, we classify things that dissolve in water as hydrophilic, water-loving. Things that don't dissolve in water, we call hydrophobic, water-fearing. And things that have parts of their molecules that have both are called amphipathic. They may have one end that's hydrophilic and one end that's hydrophobic. Does anybody know of a substance that's like this that we should use multiple times a day? Soap. That's right. What's your question? Phospholipids. Yes, that is what we will get in. Phospholipids is definitely what we are going to talk about. And soap is this molecule. Okay. In the old days, they used to take animal fat and treat it with lye to make their soap. And it's not really different. If you go to the farmer's market, that's how they make it. In the farmer's market, they might put some nice perfumes and oils in for you. But you have the nonpolar tail and the polar head. They make it a salt, so it's even more soluble in water rather than just the fatty acid. And so what happens is if you are washing your hands and you have some grease on your hands, this nonpolar part is going to get dissolved in the grease on your hand. And then the polar part is going to form cover the surface of that oil on your hand. And then when you put your hands under the water, it will wash away. It will make it hydrophilic. So we use liquid soap in our family, and I tell my children, you cannot just pump the soap and then put your hands under the water. That does not work. You have to rub that soap in to get the nonpolar part dissolved in your grease. And I try to say that to them, and then they start to scream. So they don't like anything science. Anyway, so what if you don't have soap? I mean, really, the soap is really used just to get rid of grease. But when you use the restroom, are you getting grease on your hands or bacteria, right? So oftentimes in this building, we run out of soap. Should you just not wash your hands? No. You should wash your hands. What gets rid of the bacteria is the friction on your hands and the running of the water. So just use an excessive amount of, friction between your hands and rinsing, and that should be good enough. So it's kind of gross, but it happens a lot in this building. So this is what happens with the micelle. So here we have our fatty acid. The polar part's a little exaggerated in its size, but here we have the nonpolar tail that's a zigzag. Remember, every corner is going to be a CH2, the end is going to be CH3. So this is our chain, our hydrocarbon chain, and they're going to come together so that they can be away from the water. And so then it puts out the hydrophilic head part, and that will interact with the water. That's the same thing that happens in soap. Now, we do have an attraction. The dispersion forces are holding these together as well, but really the driving force is to keep that water from interacting with our nonpolar. Here's a nice little summary of what you can expect to be hydrophilic, polar compounds, sugars with a lot of hydroxyl groups, anything that's ionic, not anything, most things that are ionic. Amino acids, those are all hydrophilic. Hydrophobic materials are going to be hydrocarbons, fatty acids, and we'll talk about cholesterol later on. Any questions about our summary of intermolecular forces? How many people are going to have to go back to Chem 1 stuff? Some of you? Yeah, a little bit? I think it's worth your time to go through and remind yourself of those things. Yes?
Chapter of this in the biochemistry book?
This should be covered in Chapter 2, but I think our textbook is a little bit more bio-based than this course is. This course is a little bit more chemistry-based than the textbook. So that's why I'm pointing you back to the general chemistry textbook. We do have copies of them in the Science Center, in the library, and if you pick up the science book or the chemistry book from the study center, it's Chapter 11 that you want to look at. Acids and bases. A little bit more review of Chem 2. Before it's Chem 1, now we're reviewing Chem 2. We're really bringing everybody up to speed so that we can all be on the same page when we talk about our reactions. Remember, very basically, an acid is a proton donor and a base is a proton acceptor. So what is water behaving like here on the reactant side? What is it doing? It's giving up a proton. Now this H plus is a proton. You can, and what I will do in class is I will call this a proton, hydrogen ion, or if it's with another water molecule, which it is in nature, it will be a hydronium ion, H3O plus. So what do you see in the structure of an acid? What will you always have in the structure of an acid? Yes? A hydrogen, yeah. You're not going to have an acid without a hydrogen. And more importantly, that hydrogen is going to be able to be ionized. It's going to be able to be donated. So we'll look at what makes that hydrogen, the acid hydrogen, ionizable where other hydrogens will not be. A base will be a proton acceptor. So if you look at this reaction going in the reverse way, so say we have an arrow pointing the other direction, the hydroxide ion will accept the proton to become water. And so this is a base. Now, in biochemistry, we do not have strong bases. We have strong acids in our stomach, but we don't have strong bases. So you're not going to see any sodium hydroxide, calcium hydroxide, any hydroxide-containing bases. What kind of bases are we going to see in biochemistry? What atom will we have on the molecule for a base? A nitrogen. A nitrogen will classify it as a base. So if you see a molecule that has a nitrogen on it, it might be a base. If I give you a multiple choice question and I say which one of these is a base, look for the one that has the nitrogen. I don't know if I have that on the test. I haven't written it yet. Now we have strong acids and bases, and we have weak acids and bases. And you can think of the strength of an acid as how many protons it donates. So if we have 100 acid molecules, for a strong acid, all 100, or pretty close to it, will donate its proton. So close to completely ionized. So all of these molecules here, all of these acids, will give up their hydrogen ion. So when you put HCl in water, you don't have the hydrogen with the chloride anymore. It's completely ionized. So we see the arrow going the single way when you put it in water. Similarly, a strong base will be completely ionized. So notice that our strong bases all have the hydroxide in their structure. We're not going to see them. So you put sodium hydroxide in water, it completely ionizes to, or dissociates into sodium ions and hydroxide ions. What we do have a lot in biochemistry are weak acids. And so for a weak acid, say we put 100 weak acids into a solution, only less than 1 to 5 of them will give up their proton. Most of them will keep it. So here is acetic acid. You put that in water, and I tried to do this with the size of the arrows, showing that really we don't go in the forward direction very much. So if we have 100 acetic acid molecules, only maybe one, less than one, will become ionized. Now, because we have an equilibrium between the acid and where it's donated the proton, we have what we call an acid and conjugate base. It's a double arrow, meaning that the reaction can proceed in both ways. So if we look at it with our head going this way, all right, this is the acid. We can see that this hydrogen goes onto this molecule. See? The hydrogen's gone, and it's now gone onto the water molecule, creating, now this is the hydronium ion. Can we turn those lights off? I'm sorry. But if we turn our heads the other way and look at the reaction going this way, you can see what's going to happen. This molecule is then going to take, will accept a proton from our hydronium ion. So our acetate ion, our conjugate base, will be accepting a proton. So we have what we call an acid and conjugate base pair, where they behave the opposite way on opposite sides of our reaction. Now I've tried to quantitate with this sort of arrow how much gets dissociated or ionized and how much goes back the other way. But what is the parameter, the description of how far the reaction goes? What is that term? We calculate it, and it has a K. Equilibrium constant, right? It's the equilibrium constant that's going to tell us the ratio between the products and the reactants. So we have this acid conjugate base pair, and then this is also an acid conjugate base pair. When you look at them, what is different between the acid and the conjugate base in both sets? What's different between them? One hydrogen ion, right? And which has it? The acid or the base? The acid. So it's not tough to figure out what it is and a conjugate acid-base pair. You look for the pair that only differs by one hydrogen ion. So I'm telling you that there will be a trick, most likely be a trick on the exam, where I show a pair that has 2 protons different, right? They're not going to be a conjugate acid-base pair. They can only differ by 1. And the one with the hydrogen is going to be the acid. The one without it will be the base. Now, can a strong acid is not going to behave like this because the reaction is only going to go in one direction. So we're going to quantify the strength of our acids by looking at the equilibrium constant. Now remember, our short term for a weak acid is HA. We're not trying to laugh, this HA. And we draw the double arrow to show that it's a weak acid, that there's an equilibrium between the ionized form and the intact acid. And remember that an equilibrium constant is products, the concentration of products over reactants. These brackets mean molar concentration. Now we don't have, an acid only behaves like an acid in water, unless it's a Lewis acid, which we talk about in organic chemistry, but we're not going to be, we're in an aqueous environment in biochemistry, so we're not going to be talking about those types of acids. But an acid only behaves like an acid in water. So we take water out of our equilibrium constant and make it a Ka. So this is really the correct form where we include water in it, but no one really does that. We just do this where we show the weak acid ionizing to the proton and the conjugate base. The A minus is the conjugate base. So it's this concentration. Now, a strong acid will have a large or small Ka. A stronger weak acid, sorry. A stronger weak acid will have a larger or smaller Ka. You don't be proud of your knowledge. It will have a larger because it will donate more protons, and therefore this number over here will be larger than what we have here. Most of our weak acids are really weak, and so the number on the concentration of the hydronium ion and our conjugate base is going to be much less than the concentration of acid that you put in there. Acetic acid is in vinegar, 5%. We can eat that. It's not going to denature the proteins on our tongue or in our throat. So it's very weak. So in neutral, so for water, what we have is this thing where it is going to react with itself. So remember we said water can dissociate into hydrogen ions and hydronium ions. Let me see if I can write this up here. Okay, so here our Ka is going to be the products over the reactants. The molar concentration of water in water, if you just have like a liter of water, it's 55 molar. So we know that. So if you have pure water, it's 55.5 molar. So what we do is in pure water, we define something called Kw, which is just the Ka here times 55.5. And so our Kw is the hydrogen ion times the hydroxide ion, and that equals a Kw. Now what's interesting is that this value is always the same. In pure water, we have hardly any hydrogen ion and hydronium ion. Our water only dissociates to the extent where the hydrogen ion is 1 times 10 to the minus 7th. So you go from 55.5 molar here, and you only have 1 times 10 to the minus 7th molar here. So that's a huge difference. So it's really negligible in pure water. We have almost all water. Now this value, when you multiply the two, is always going to be the same. And what's interesting is that when we raise one, we're going to lower the other one, so that when we multiply the two, we always get 1 times 10 to the minus 14th. That's our kW. Now, to make things easy, so that we don't have to express things in molar concentrations, we're going to define the P function of this hydrogen ion concentration. And a P function is just the negative log. So we can take the P function of many things, but we're going to take the P function of our hydrogen ion concentration, and that's going to be the negative log. And so when we take the negative log, or the P function of something that's big, it makes a little number. So when you have a strong acid, you're going to have a lot of hydrogen ion around. So you have a big number there. What is the pH going to be? It's going to be lower. So that's what the P function does. It takes a big number and makes it little. So again, at neutral pH, pure water, we are always going to have 1 times 10 to the minus 7th molar for each of them. But if we're in acid conditions, our hydrogen ion is going to be larger. What happens is the hydroxide ion gets lower, so that when you multiply the two, we still get 1 times 10 to the minus 14th. So in acid solutions, we have greater than 1 times 10 to the minus 7th molar, and then the hydroxide ion concentration goes down. In basic solutions, we're going to increase the hydroxide ion concentration, and that reduces the hydrogen ion concentration. So again, in acid solutions, our pH is going to be low. In basic solutions, our pH is going to be high. Because in acid solutions, we have a large hydronium ion concentration, larger than 1 times 10 to the minus 7th. And so that's going to make a low pH number. In basic solutions, we're going to have lower than 1 times 10 to the minus 7th. And so that's going to be a higher pH. So remember that relationship between the concentrations and the pH value. So what is the pH of a neutral solution? 7, because 1 times 10 to the minus 7th, if you take the negative log of that, it's going to be 7. When you take the log, you're really looking at the exponent on the 10. If the coefficient is 1, then it's just going to be the coefficient on the 10. We're going to take the negative of that, so that's the negative before the 7 becomes a positive. So we use a lot of acids and bases in our life. One thing I want you to notice is that we eat a lot of acidic stuff. They have coffee. Black coffee is pH 5, right? But I have some milk in here, so it's going to bring it up, well, half and half. It's going to bring it up a little bit. So I'm drinking something acidic. It's probably not good for my teeth. And then bases are kind of nasty, right? Ammonia, hair remover, oven cleaner. All right, those are basic. We don't really eat a lot of those things. And neutral, again, is going to be that pH. So pull out your calculators. And let's do some work with our pH values. You don't really need, for the first set, you don't need a calculator. So if we have a hydronium ion concentration of 1 times 10 to the minus 7th, our pH is 7. One thing that's interesting for sig figs is that if you look at this concentration, 1 times 10 to the minus 7th, how many sig figs do we have in this value? 1, right? You look at the coefficient, and that's a number of significant figures. So here, this power of 10 is reflected in this number. But that's not a significant digit, right? So when you're doing pH, the number of points of digits after the decimal is a number of significant figures. I am not going to test you on that, okay? If you calculate pH and you give me a number that doesn't have like 15 digits, then I'm going to be good with that, all right? But I just want you to know the right way. So here, what is the pH going to be? 5, yeah. You guys still asleep? Rough weekend? Yeah, rough weekend. There was no football, right? So, all right. This one's going to be, of course, 10. Well, what if this coefficient is not 1? Yikes. It's going to be, you're going to look at that exponent, and it's going to be somewhere between that exponent and one number less. So here, the pH is going to be between 4 and 5. But I want you all to put into your calculator or your phone, hopefully your calculator. And if you have an iPhone, you have to turn it sideways to get the log. And try to get the pH. If you have your crazy high school calculator. Do you really need that for high school? Do they use it? The graph. Yeah, she's taken all the math.
Still use it though.
Yeah, I know. So what'd you guys get?
4.6.
So 2 sig figs.
Wait, how did you do it?
4.56.
I got 4.59. Yeah? 2.6 times 10 minus 5th. So sometimes you have to do, like probably on the iPhone, you might have to do log, and it will give you already a parentheses. And sometimes you might not know how to do exponents. So you might, for now, write in 0.000026, and then the other parentheses, right? So if you're not using a real calculator, it might be a little bit different. So write down, click in log, and then write 0.0, so 4 zeros, and then 26, and then the closing parentheses. I want to make sure that everybody can get that. And if you didn't bring in your calculator today, I want you to go home, find your calculator, or buy a calculator, and practice this. I need to make sure that you're going to be ready to do this on the test. Yes? 4.59. Yeah, if you don't have your calculator, be sure to write down the answer. If you're having trouble, you can ask your neighbor here. If you're using a graphing calculator, I have not yet figured those out. I suppose I will be over the next year. Although she's using it now for algebra, so. No, she's not asking me for help, so I don't know if I'll learn how to. She's got that one. It's not that hard.
Us in school.
Huh?
So I remember having like a lesson in school.
In school, they show you. Okay. All right, everybody able to get this? 4.59. How about this one? It should be between 8 and 9, right? So this is, you should always ask yourself, what is the reasonable number? So this one's going to be between 8 and 9. So make sure that you're looking at this. 8 point something something, right? You said between 8 and 9, because the exponent is 9, negative 9, so the pH is going to be between 8 and 9. So this is how you're going to check your work for the exam. What'd you guys get? Yeah, 8.20. And this last one, what number should it be between? 2 and 3, yeah. I got 2.11. Good. So 2.11. Make sure you write those down. And especially if you don't have your calculator. I'm not going to let you use your phone as your calculator on the exam, obviously. How about the other way? What if we're given the pH and we want to know the hydronium ion concentration? This is a little bit more difficult. You're going to do 10 to the x. Does everybody see on their phone or their calculator 10 to the x? So what you're going to do is 10 to the x of the negative pH. So try this. Orange juice is pH 3.5. Isn't orange juice really bad for you? It's a lot of sugar. It's good sugar? So it's okay to... Yeah, they have in my house like a glass like this. Yeah. That's like 4 oranges, yeah. We stay pretty healthy, though. I think it's because we're outside a lot. All right, so 10 to the negative 3.5. Try that. Oh, I didn't put any of the answers. So you know that it's going to be something times 10 to the minus 4th, right? Because of the backwards way. The pH is going to be the exponent between the exponent and 1 less. So if we have the pH of 3.5, the exponent is going to be 10 to the negative 4th. So I see my, is it 3.70? 76? Oh, 3.16 times 10 to the minus 4th. 3.16 times 10 to the minus 4th. Did anybody get that? No. Do you see the 10 to the x on your calculator? So do 10 to the x, and then negative 3.5, and then parentheses again. Is it not working? Or you might have to do negative 3.5 and then 10 to the x. Try that. How'd you do that on the iPhone?
You put in the number first.
Oh, you put in the number first for the iPhone? Okay. Again, iPhones aren't going to be allowed on the test. All right, how about this one? Try this one again. So negative 6.2, 10 to the x. John's got my favorite calculator. It's easy. You don't need more than that. $10 at Walmart, right? And this one is something times 10 to the minus 7. What is that number? 6.31. So 6.3 times 10 to the minus 7. Excellent. If you guys are still having trouble, you can come see me after class, and we can work it through, especially if you have your calculator and you still can't get it. I'd love to work with you on that. And then if I can't figure out your calculator, we might have to go over to the Learning Assistance Center. All right. So let's remember that a weak acid does not ionize completely. And we have it in small amounts of its conjugate base in solution. If we add in more conjugate base, as in a solid, like the salt of it, in order to have significant amounts, then we have to consider that concentration of conjugate base when we're calculating the pH of the solution. And we do that through the Henderson-Hasselbalch equation. I've asked my general chemistry students to tattoo this equation on some part of their body. No, you don't have to do that. That might get you some extra credit on the final. Anyway, so just sit back. You don't have to really know anything from this slide except the Henderson-Hasselbalch equation. But what I'm going to do, I'm not going to require that you derive it, but I'm showing you that it's really not a tough equation. Really, we're doing is putting it in a usable, an easy to calculate format. So we start out with the Ka when we have a weak acid, products over reactants. Then what we're going to do is take the log of both sides. And so we're going to take the log of the Ka. And when you multiply things, you add the logs. So we can do the log of the hydrogen ion plus the log of the ratio of the base to the acid. And so then what we're going to do is, oh, there's something wrong here. Oh, okay, no, there's nothing wrong here. Then what we're going to do is then take the negative log. So we're going to move this to this side of the equation. So move the log of the hydrogen ion over to this side of the equation. That makes that negative. Or, another way you can look at it is that we're subtracting the negative log from both sides. So that moves over to this side, but we have now negative log. And then we're going to move the log of the Ka of that acid, which is a constant, you can look it up, over to the other side. So we have the negative log of the hydrogen ion equals the negative log of the Ka plus log base concentration over acid. And so the negative log of the hydrogen ion concentration is the pH, negative log of the Ka is the pKa, and the log of the base concentration of the acid. And I remember this by birds on top and then ants on the bottom. Right? Remember? Isn't that how we did it in general chemistry?
Yeah.
So birds and ants. I use that later on, birds and ants, later on in the semester. But that's how I remember Henderson-Hasselbalch. I'm not going to give you this equation on the exam, but I want you to know it.
We're going to have to do like math with you?
I have to check. It's going to be simple math with these. So it's not going to be like in-depth math. So just like the homework, it won't be harder than the math that you have to do in the homework with this.
You're going to give us the pKa.
Yeah, I'd have to give you the pKa. So the pKa is, just like the Ka, is something unique to each acid. It's something that characterizes the acid. So if the Ka of a weak acid is big, then what is the pKa going to be? Small. So you can think a stronger weak acid is going to have a lower pKa. And that makes sense in my head because it has a more acidic pKa, a lower number. So that makes sense if I'm going to sort of classify acids. So we use this when we have significant amounts of both the weak acid and the conjugate base. What is that called when we have significant amounts of the weak acid and the conjugate base? What do we call that type of solution? I'm going to start to cry. It starts with a B. A buffer. Yes, thank you. You saved me. It's a buffer. A buffer has significant amounts of a weak acid and the conjugate base. I'm sorry. When the weak acid equals a conjugate base, when we have same concentration of the base and the acid, what does this log become? It's a log of 1. What is a log of 1? 0. So the pH equals the pKa when those two concentrations are equal. When we have a pH that is lower than the pKa, we have more acid. When the pH is above, we have more base. That makes sense, right? So here we have the pKa. That is a value that we get when we have equal amounts of the base and acid. If we have more acid, it's going to make the pH go down, right? Below to more acidic pHs. If we have more base, it's going to make the pH go up. So the Henderson-Hasselbalch is going to help us calculate the pH during titrations. Do you remember those fondly?
200.
Yeah. If you took analytical chemistry with me, you did 500. And buffer solutions, more importantly. And if you can believe it, what time is it? All right. We're going to take a break and come back and talk about titrations. Hold on.